Okay, related rates. This is really tricky. This is something that most people struggle with. So I'll do my best here for you. Um, First of all, the title actually gives you some clues as to what we're actually doing. So the two words that are related and rates are actually really important. First, I want to mention this word rates. So a rate is some value divided by an increment of time, miles per hour, gallons per minute, whatever the case is, right? And so it's something over time. So when we think about um, calculus and derivatives, that's a d something over dt because this is a change in time, right? And so t in for related rates, we're always using t because something is changing. We're asking the rate of change. So it could be a dy dt or a dx dt, dwt, dA dt, just something dt. That's the rate part. The related part is equally important in that what we're saying is the variable that we want for our answer and the variables we're given in the problem have some kind of a relation. And the relation is meaning they're connected via some kind of a formula. The formula could be something like area of a circle, Pythagorean theorem, a trig derivative, volume of a sphere, whatever. There's some kind of an equation that relates, and you notice in each of these examples, there's multiple variables. So over here I have A stands for area, R stands for radius. So, and if you think about it, if a radius of a circle is changing, the area is also changing. So those two things have a relation with each other. Same thing with an angle, right? If an angle is changing, that means the triangle is shifting. The side lengths are shifting. So that's the big picture for related rates. That's what we're doing. Let's look at a couple examples here. And I'm going to give you some steps. These are my steps that I use for these. As you get better, you can, of course, modify these however you want, but I'm just going to give you my method of doing it. So first, the trickiest part is these are always given as word problems, which everybody, word problems, they panic. So what I ask everybody to do when you're looking at the word problem is first thing is find in the word problem, what's the question? What are they asking you? And there'll be a question. What is the rate of change of the radius? Or how fast is the volume changing? Or something like that. That's the variable you're looking for, and that's what the dt part is. So for example, how fast is the volume increasing would be a dv dt. How fast is the angle changing? d theta dt. So you have to look for that. So when you do your implicit differentiation down here in step 3, you know what you're looking for. And if you happen to use a wrong formula and you don't see this thing you want in it, then you know I need to back up and find a different formula. Super important. If we're thinking in engineering terms and physics terms, we need to be careful with our units and then what variable is available for you. And probably you'll need to draw a picture and label it appropriately. Most of the time we need a picture for doing related rates. Step 2 then, once you do that, is to find the formula that we need to solve the problem. We're going to take the derivative of that formula implicitly with respect to t, and then check again, like I said, that your rate you're looking for is in that implicit derivative. Then I call it plug and play. Just plug all the information you have in and then solve. All right, so let's look at some examples. So here we have a balloon is inflating at 2 cubic centimeters per second. So that is the rate of volume change. And then they want to know how fast is the radius increasing when the radius is 3 centimeters. Okay, well, step 1 was, what's the question? Here's the question. How fast is the radius changing? So that means the variable I'm interested in is r. And then that means that the answer I'm looking for is dr dt, because that's the rate of radius change. So that's what I'm looking for. So I need to come up with an equation that I can get after the derivative. It has a dr dt in it. This up here is a volume change, meaning that variable would be a dv dt. So I have some information here. And then here's an r. That's my radius change. So it sounds like, since we're talking about radiuses and volumes, I would need to know the formula I'm going to use, step 2, is volume of a sphere. And volume of a sphere is 4/3 pi r cubed. And if you say, well, I don't know that, well, your teacher might give that to you, or that might be something you might need to memorize. But in any case, that's the formula for that. So now, once we have that, we're going to take the derivative of that. So we take the implicit derivative with respect to time. So the derivative of v is dv dt. 4/3 pi stays there. The 3 comes down. So r cubed becomes 3r squared dr dt. So here's where we are. And this is the spot where we want to check. Do you have that variable that you were looking for? And ours was dr dt. There it is. So that's what we're trying to solve for. So from here, we can simplify and plug and play. Just plug things in. dv dt, that change in volume, came from the problem itself. I can simplify that to 4 pi. I can plug in the r. That came from the problem itself. And then I get this side is 36 pi. Divide both sides by 36 pi. And then that's my dr dt. That's the answer. So the radius is changing at, well, 2 over 36 pi is 1 over 18 pi. So that's the rate of change of the radius. Here's another one. Here we have a tower over here. We have a person who's 3,000 feet away from the tower. We have an airplane that is flying at 4,000 feet. And at the moment it's over the tower, how far is the straight line from the plane to the person? And the plane is flying at 600 feet per second. So we look at this and we think, oh my goodness, obviously we need to draw a picture here. And the thing we're looking for, I've just labeled it as x here. The thing we're looking for is this length changing. So if I label this as x, you can label it whatever you want, but I'm calling it x, meaning the rate of change is dx dt. So we have to figure out some kind of a formula that I can get a dx dt out of. Now, this looks like Pythagorean theorem to me. And so we can say, well, let's set it up like that and see what happens. So I have the Pythagorean theorem would be, I'm just going to label this side as a and this side as b and that side as x. So it would be a squared plus b squared equals x squared. But something important to think about in this case is that b is never changing. So if I were to take the derivative of it, it would be 0 because it's not changing. So I can actually just plug in that value here. So a squared plus 4,000 squared equals x squared. And if you were to go ahead and plug in b squared, it would work out the same way anyway. So don't think this is the only way to do it. When you take this and take the derivative here, so here's our a squared plus 4,000 squared equals x squared. So the derivative of a squared implicitly is 2a dA dt. This is just a number which goes to 0, so that goes away. And the derivative of x squared is 2x dx dt. Aha! There's our dx dt. That's what we were looking for, so we're on the right track. From here, we just start plugging things in. So a was that length of a, which we knew what it was, 3,000. And the dA dt, this problem's a little tricky because the plane's up here, right? And you think, oh, this is a fixed distance. The guy is this? No, this is actually the distance on the ground from the plane directly overhead to the guy. So it just so happens that right here, it's here. As the plane moves over this way, that distance is going to increase, right? It's the plane on the ground is farther away from the guy. So that was a little tricky in that problem. So the plane's velocity is 600. And then we say 2x. Oh, we need to actually know what x is. I don't have x. And there's the dx dt. So frequently when you're doing related rates, you're going to come across one variable that you don't have. And then we need to stop and say, can I get that variable? And the question is, yes, I can. So in this case, I can calculate x at that moment via the Pythagorean theorem. And obviously, my friends, this is a 3, 4, 5 right triangle. 3,000, 4,000, 5,000. So x is just 5,000. So I can plug that in here, resume the problem, divide everything out, and I get 360. So the distance, the straight line distance from the guy to the plane is changing at 360 feet per second. So that's while it's moving that way. Okay. A trickier one. So this one involves a rocket is being launched over here, and there's a camera. Camera's 5,000 feet away from the launching pad. The rocket is launched. When it's 1,000 feet in the air, it's traveling at 600 feet per second. And we want to know, this camera has to track it, right? So the camera, this angle has to open up as it's tracking it. And we want to know at that moment, how fast is this changing? So notice that this velocity can be translated to a dH/dt, that this is changing here. And since we're talking about an angle changing, this would be d theta dt. So we have to think of what can relate theta with with h. And that's a trig function, right? And in this case, we don't really need to know the hypotenuse. We don't even have it there, so we don't need to worry about it. So in this case, we're just going to say, oh, that's easy. The tangent of theta is opposite over adjacent. Oh, so h over 5,000, simplify that. So I get 5,000 tan h equals, 5,000 tan theta equals h. There's our formula. Go ahead and take the derivative of that. So 5,000 secant squared theta d theta dt, that's chain rule there. Be very careful. Remember, the argument doesn't change. Here, don't change that. Some friends are going to want to say 5,000 secant squared d theta dt. No, this argument does not change. You keep that there, and you add the d theta dt equals dh dt. So we have dh dt. It's 600. So let's see where we are here. We have the 5,000. That's our target. That's what we want. We have the 600. We don't know what the angle is. What is the angle at that moment? Well, many different ways to skin this cat, but let's look over here. So at that moment, we said it's 1,000 feet in the air. So then we want to know what is that angle. So we can say, well, the one way to do it, there's other ways, but one way to do it would be say, what's the arc tangent of, I wrote that backwards, oops, of this, of 1,000 over 5,000, and it's about 11.31 degrees is our theta. And then for this, we want to know what's the secant of theta. We want to actually do the math. Well, remember, your calculator doesn't have secant, so I'm going to compute what the cosine of that is, and then take the reciprocal to find the secant. So a little bit of trig shenanigans we have to do here, and then I'm going to square that. And so I get about 1.04. Multiply that by this and divide, and I get about 8.67 degrees per second. You can certainly do this in radians if you wanted to. I'm not a radian person, so I care not to do that, but you certainly could. You could also compute the secant manually if you wanted to by going ahead and using the Pythagorean theorem to find that. Compute the secant manually. There are lots of different ways to do it. Oh, the funnel one. Yikes, my friends. These are tricky. These are so tricky. So let me say why they're tricky. Just look at the formula for the volume of a funnel here. It's 1/3 pi r squared h. So the problem is you get two different variables. And you know that if I just took this and found the derivative that way, I'd have to use the product rule. So I'd end up with an r, a dr dt, and an h and a dh dt. So you're adding all sorts of variables here that you may not need to or want to. So the funnel, the trough, those are very common Calc A, B, B, C questions on the test because there's a trick. And the trick is the relationship between the radius and the height, that you need to solve one for the other to get your answer simply. So let's look at our problem here. So we have a funnel. It's draining at 0.03 cubic feet per second. The top of the funnel, it's a 2-foot high funnel with a 1-foot radius. And we want to know how fast is the, what are we solving for? How fast is the height changing? We want to know how fast the height is changing when it's a foot high, when the liquid is a foot high. So here is our function here, but we want to switch this either to r's or h's. So the relationship of the funnel is that this similar triangle is preserved no matter how high the water is. So I have the height is equal, in this case, 2r equals h. So there's this relationship that I can use to substitute in here. So look, 2r equals h, so I can plug the 2r in here for h and solve, and now I only have one variable. So I'm going to go ahead and take the implicit derivative, and I come over here and I get a, I get a dr dt. Wait a minute, I don't want this question would be how fast is the radius changing? Oh, I don't want that. I want dh dt. So I'm not going to use this substitution. I'm going to use this substitution. We want dh dt. So instead, I'm going to substitute and get the r out of there. So if 2r equals h, then r equals h over 2. So I can substitute this way. So h over 2 squared, which is h squared over 4. Do some simplification here. Pi over 12 equals h cubed. So now I can take the derivative here, and I get pi over 4 h squared dh dt. There it is. There's that dh dt. So that trick is that little extra thing that they're doing to, just to see if you're paying attention. And then we can substitute from there. We can substitute everything in. We had the height was a half a foot. Here's the volume. And we do our work, and then we come down here. So the height is changing at negative 0.158 feet per second. There we go.